Hello everyone, welcome back to our YouTube channel. In this episode 3 of the Pathway Analysis series, we'll be discussing the concept of overrepresentation analysis, the ORA. Now, the content of this presentation would be as follows. We'll first discuss what overrepresentation analysis is. We'll look at the workflow of the overrepresentation analysis, and then we'll look at the concept of the gene list versus the background list, and would also lastly we'll look at the Fisher's exact test or the hypergeometric test and into more details. Now, when we talk about ORA, we are testing whether proteins associated with a disease or like a particular biomarker are concentrated in specific pathways more than we would expect by chance. For example, out of 1,000 measured genes, 90 are significantly linked to, let's say, colorectal cancer risk. That is the particular biomarker that we'll be looking at. And we are saying that are those 90 randomly scattered across pathways, or do they cluster around a few like inflammation or immune signaling pathways? Now, ORA answers this particular question using a simple discounting argument formalized with the hypergeometric distribution or the Fisher's one-tailed exact test. When it comes to the workflow of the ORA, we have like an experiment where those ones are done in the lab, where you get to find the associations of proteins or the genes with the particular biomarker that you are looking at. Now, after running those tests, what we'll do is that we'll define a background and a gene list. Now, the background set will be the totality of every measured gene. So every gene in the experiment would be included in the background set. Now our genes set will be filtered by a p-value or the log 2-fold change, or like any threshold that we'll decide to use. Now, in doing this ORA, it is expedient that we choose a particular database that we'll be using, which could be KEGG or Gene Ontology, which is the GO, or the Reactome, or any other databases that are available. Continuing with the ORA workflow, we have the building of the 2x2 contingency table for each pathway overlap. And then next would be the inculcating of the multiple correction methods such as Buenferroni or the Benjamini-Hochberg, or any other correction method that you can use. And then we'll move on to performing the statistical test like the Fisher's exact test or the hypergeometric test. And then the last step would be to interpret whichever results that we have. Now, moving on to the differences between the gene list and the background list, we are considering the background to be every measurable gene. In, for example, when we conduct an RNA sequence experiment, every measurable gene that was measured in that particular experiment would be in our background list. Now, with the gene set, we are looking at a subset of meaningful change genes. So the subsets, the genes that showed meaningful change in our experiment, which we will be extracting by using either p-value thresholds or log 2-fold change thresholds to deduce the subsets from the particular background set. So in summary, we are saying that the background is the set of all measurable genes in our experiment. Now the gene list will be the significantly changed genes in the background list, okay, and per the particular threshold that we would use. Now, to the Fisher's exact test, what we are doing is that we are measuring whether the overlap between a pathway and a foreground, in this sense, the gene list, is larger than expected by chance. So for each pathway, we'll build a 2x2 contingency table. Now, in the table, you would see that the column has in pathway and not in pathway, and on the row sides we have the significant versus the non-significant. Now the variables in this particular test are number one, the general universe, which is the background set, which is N, and now we identify the query set. In this case, the query set would be our gene list, and it would be denoted by small n. So the background is the capital N, and the gene list will be the small n. Now, for each pathway, the size of the pathway will be denoted with the capital K, and now the overlap between the pathway and the gene list will be denoted by the small letter K. From there, we'll compute the hypergeometric the one-tailed p-value from the hypergeometric test, and we'll also apply the multiple testing correction. So when you look at the Fisher's exact test, you would see that we are calculating the p for which x equal to k, and it is given by the combination of the size of the pathway and the overlap between the pathway and the gene list times the combination of the background minus the pathway, the size of the pathway, and then the gene list minus the size of the overlap. Okay, so and we'll divide it by the combination of the capital N, which is the background, and the gene list, which is the N, and then would compute the enrichment p-value as given in the formula below. So that is it for the overrepresentation analysis test. In our next video, we'll look at the gene set enrichment analysis, which is also one of the methods of pathway enrichment analysis. We'll also look at the enrichment score. Stay tuned to learn more, and we are glad to have you here. Bye bye.